being accurate. Predictive maintenance cost model, actually it's the output of pre-domain project. A follow-up paper also will be presented in a conference. So the stage is up to you, Dr. Florian. Please start.
Yes, thank you, Marco. Thank you very much for the invitation to give this presentation. It's a big pleasure to present this work since we both developed it in a joint research project. This was during your stay at the SCCH. This is, let me quickly introduce it. It's a non-profit research organization in Austria. And it has about 124 currently employees. It's growing pretty quickly recently, and we're going towards the 25-year anniversary. It's, as Marco knows very well, kind of much located in the countryside. So the software park that has been founded in this year 1999 is growing quickly, but it's really away from the next big city, which is Linz, and still, however, connected to the university there in some way. And the typical activity is service research for producing companies, and we are Marco and I were together in one project concerning predictive maintenance, which is, as you know, the strategy of performing scheduled maintenance in a way that looks at the specific situation and applies learning models to then come up with most optimal schedule for repairing things, maintaining things, and putting things into the next maintenance cycle, so there will be uninterrupted production. This is the project that we have been together in. It's an international project funded by European money. It's involved these partners, and we were really performing tests on ball screws that are these devices that are translating a rotational movement of these screws into a translational movement of something that is attached to it, and they're mounted on ball bearings. And we investigated how much wear-related deterioration of this device would be visible in advance. So we would apply heavy load to such a test bed, and then measure how long we would need to break the device and how well we would be able to anticipate it in advance. And so such experiments were conducted. Maybe it's a fun fact to remember that we needed much longer to break it than expected. So that was one of the difficulties in gaining data. The device was pretty sturdy, and we needed to increase the load by much more than we thought. And so obtaining good data for training our learning models was somehow difficult, and well, also reflected the difficulty that many companies have. Our concentration was on small and medium-sized enterprises, and we wanted to investigate what are the conditions for predictive maintenance to be used in a profitable way, and in a way that even a small enterprise can invest in by accepting the associated investment risks. So this is what we will talk about in this presentation. We developed a predictive maintenance cost model to compare different strategies and compare predictive maintenance as in particular to conventional or more classical strategies for maintenance. And the whole work is already sent into this conference. It's called the European Network for Business and Industrial Statistics, has an annual conference happening all over the world, and this time it will be in Spain, and our contribution has been accepted, and we will be in the category predictive modeling, I think. So this is the setup, the framework, and I would like to now start with some basic facts about predictive maintenance and how we tackled the question of showing that predictive maintenance is in fact a profitable strategy, and under what circumstances, however, this is true, and which conditions have to be met. So in fact, also companies with low budgets can lift the risk that is associated with these investments to actually obtain the know-how to invest into human resources and to invest into the corresponding technical setup, so that sufficient data quality and sensor quality to collect data is established. And of course, these things are associated with considerable financial burden. And so the question is, when is the point of return of these investments given, and can we be sure that using predictive maintenance instead of a different kind of maintenance strategy actually eventually pays off? So this is the question that we're asking here. Let me start with reviewing some really classical maintenance methods. Recall that if you run your car until it breaks down and then you take it to the mechanic and to the repair shop, that will be called reacting to a breakdown, and that means that it is in a certain way pretty ideal because you're maximizing the uninterrupted time of use of your car. And if you're lucky, this is happening only late. But think of now a process in which cycles are much more frequent. The maintenance cycles are happening more often. Then even if sometimes you're lucky, it will turn out not to be essential in what happens sometimes. It will be essential in what happens typically. So if there is a certain distribution for the recurring breakdowns, and we will take the view that the cycles are, in a stochastic sense, always identical. So whatever happens over and over again, it's, so to speak, the same random variable, and so it's a stationary stochastic process. Under these circumstances, it will be important to react to the specifics of the breakdown distribution. And one of the possibilities to do so is a more advanced maintenance strategy called the preventive maintenance strategy. This is studying the typical behavior of maintenance in the sense that one fixes a deterministic and always the same time after a maintenance cycle has been started, and it occurs, the maintenance, after the same production time has happened. And in the case that one chooses this time wisely or well, then it means one is actually um, uh, predating the breakdown, and this is what can cause significant advantage over the reactive maintenance, in the sense that the breakdown occurring at some unforeseen moment in specific lets the maintenance cycle, maintenance routine, to be scheduled in advance. The corresponding time to do it can be minimized. It can be minimized in terms of cost, because of the corresponding parts to perform the maintenance are actually ordered in advance. And all these advantages of being able to schedule the maintenance before the breakdown occurs can be used to gain more profitability. Of course, it has to be realized that interrupting the production process prematurely also has a disadvantage, namely that the uninterrupted production time isn't as long as it may be in the reactive case. And so over a large amount of time, if this preventive maintenance is done much too early, one loses a lot of production time. And so this would be, so to speak, the disadvantage. This is exactly what one tries to remedy in the predictive maintenance case, where this scheduling moment isn't also chosen in the same way always. However, it's chosen by depending on the specific workpiece or the specific machine part that is in use in this specific maintenance cycle. And so that when the observation of the data suggests that in this particular case, the maintenance time may still not need to be chosen early, but can wait a long time, then predictive maintenance has the advantage that it allows to do so for the individual case, and therefore saves or gathers uninterrupted production time, in which case it is in an advantage over the preventive maintenance, where this schedule is much more simple and fixed, while the predictive maintenance schedule is adaptive and can react to situation in which maintenance is not yet needed and can wait. So these are the two, so to speak, old versions of maintenance, and the predictive maintenance has the advantage to be being better than both of these. Let me explain this in a more detailed way. Consider such local, so to speak, forms of increase of profit while there's this large flank here during a single cycle. These things are supposed to represent maintenance cycles, so they occur always at these times where suddenly the profit goes down. Of course, repairing a single item, a single workpiece, takes money. So the investments can be thought of using up a certain cost rate over a certain time. So the profit will go down during this maintenance cycle. During this constant period, that represents the idle phase. nothing happens, and it represents, so to speak, the difference in time between when the stopping of the production occurs, either because there's a breakdown or it has been scheduled to stop right there, until the actual repair occurs. This is what this horizontal part is supposed to indicate. And the whole downtime is, so to speak, a sum of, if we look at a single such maintenance cycle, after uninterrupted production has occurred, there's some idle period, and then another non-producing period in which the actual maintenance occurs at a certain cost takes place, so that for a single maintenance cycle, the red line over here represents the profit rate just over this single interval of a single maintenance cycle. And of course, these breakdowns, or let's say if we use reactive maintenance, these times at which indeed the production cannot go on is interrupted because of a breakdown, then naturally this will occur always at different times, namely when these breakdowns occur. So we can think of this production time in this case as a random variable, which has a distribution that is given by the nature of the device or the machine or whatever we are maintaining. At the same time, of course, the idle period may be random, or usually is random, because maybe a certain time has to pass before the actual repair can occur. It is probably fairly reasonable to, in many situations, consider the same cost and time for the repair. However, of course, it may also depend on what actually broke and how much needs to be repaired. So this may also be a random variable. So these 5 different values, the cost rate, the gain rate, the 3 times here, they can all be random variables. And in many cases, of course, some of these parameters are constant or reasonably chosen to be constant. And what we're interested in is not only the profit for one cycle, but some average over such profit rates over the cycles. And if we make this assumption that I have already indicated, that whatever occurs during one maintenance cycle is identically distributed, so that all these, what I just said was the times could be random variables. Suppose they are always distributed according to the same identical distribution. Of course, the realizations are always different. Then what we have is so-called, and let's say also this is independent each cycle, then what we have in this case is a so-called renewal process. So at the end of such a cycle, the sum of these times will be a sum of new independent but identically distributed random variables. So the time of which it takes for one cycle is a renewal process. The same is the case for the profit for one cycle. And so this is the case for the rate as well. And as you can see, this sketch over here indicates that it is very well possible that, or most likely that, the single gain rates or profit rates for single maintenance cycles are different, but under the assumption of this renewal property, we know that they, if we, so to speak, average this, approach a constant deterministic non-random value. And what this means, we'll come to in a second, what kind of average is meant here. I hope everything so far makes sense. Summarizing so far is we have some input values for the corresponding maintenance cycle, and what we're interested in is the profit rate in the asymptotic case. So in the case where we divide the gained profit after some time by the corresponding time needed for this gain. So using this idea, we will eventually come to a limit law that allows us to take expected values of these parameters and determine the asymptotic profit rate. Before I come to that, I would like to discuss the three different maintenance strategies that we have mentioned in the beginning. With this sketch here, we already observed that the production time may be ended due to some breakdown occurring before some prematurely before some maintenance is carried out. So this would be the case of reactive repair or maintenance action in this particular case. Of course, also it's possible that, and we will call this alpha, scheduled maintenance time predates the breakdown, which means that alpha is smaller than or equal to beta, and this means that one either by choosing it deterministically, then it's a very simple random variable, or by choosing it independent of beta, one is able to achieve this, that the production time is ended because one scheduled a maintenance that predates the breakdown. And so those two cases can occur, that alpha is less than beta, and the other one that alpha is larger than beta. If it's just beta, then we are aware that this represents just the reactive maintenance case. If it is chosen to be smaller by some schedule, then it's either preventive or predictive maintenance. It is predictive if it's not a deterministic constant, but it's actually some estimator of a time that is, supposed to be predating beta. So here is where AI comes into place. If we observe this process, and I'm now using these indices I for the ith breakdown, then we consider, so to speak, for a single the ith cycle, the corresponding profit, which is the production profit minus the cost of the maintenance, and this we consider in relation to the time it takes for this cycle. And of course, we can form the sum of these profits and the sum of these times and divide, look at the division of this. And reactive maintenance now means that the end of the production time tau equals the breakdown time beta. So here we don't even try to predate it, the breakdown by some chosen alpha. We just let the breakdown occur and choose tau to be equal to beta. And this is called reactive maintenance. If we try to choose tau to be smaller than some beta by a deterministic value, which is always the same for every, or not even the same, but it's chosen deterministically and not independence of the given observation of the given, random physical process that causes the wear to occur and causes the deterioration of the functionality of the machine, then we call this preventive maintenance. But tau in this case is non-random. Whereas if we allow prediction of tau to be depending on omega, and in this way allow ourselves to look at the specific workpiece omega and make the choice for the corresponding scheduled maintenance time in accordance to whatever we know or observe about this specific workpiece and item, then this is called predictive maintenance. And this is the general case, and we would like to now show that asymptotically, the profit divided by the time is larger if we take predictive maintenance, as long as we choose the corresponding distribution for the scheduled maintenance time properly. What is kind of shown over here is that in this case, the scheduled production time is happening before the time beta that it would show if we didn't do any premature maintenance. So this is what we say if alpha is smaller than beta. And also what of course could happen in this case is that the corresponding idle time is then shorter, namely that it's chosen or it's because of the maintenance can be chosen in such a way that, for example, not a weekend or something like that is happening exactly at the breakdown, so that one has to wait for performing the maintenance. So just as much as tau can be smaller than beta, it's also possible that the idle time, it's always abbreviated by a iota here, leading to a smaller downtime delta, is smaller in the case when the maintenance time predates the breakdown time. So this is something that one should keep in mind. As you see, because this is shorter, I somehow end up with a higher slope of this yellow line, and I kind of wouldn't do so if this would be as long as this iota, this idle time of the other one. I would actually end up being something like this, where the corresponding profit rate of the preventive maintenance, in this case, in this prematurely scheduled end of the production, leads to a smaller ratio of profit divided by corresponding needed time than in the reactive case. So it's possible that, as you see here, that this reactive maintenance also turns out better than some scheduled maintenance strategy. So let's see under what circumstances this turns out to be in this more favorable, more profitable case. Let us observe that these processes, because they are recurrent events, by simple considerations, lead to a limit fraction of the sum of the profits divided by the sum of the times that necessarily converges and exists as a number almost surely. Why is this the case? If these products, these P's, become large, this sum divided by n is converging due to the law of large numbers, the expected value under IID circumstances. And this is true for T as well. And the limit of two fractions, the fraction of two limits equals the limit of the fractions if the denominator limit exists and is positive. So we, under pretty simple conditions, have with this definition an existing limit, and we call that the asymptotic profit rate. That's, so to speak, what we saw before. It is also under general conditions true that as long as I have a renewal process, even if these values, these parameters are not independent for a single cycle, then I still have this existence of this limit. So this is true under quite general conditions. If we have a renewal process, I am introducing the symbol with the wedge. This is, so to speak, the minimum of those two numbers, namely the minimum of the breakdown time and the scheduled uninterrupted production time. Alpha is, if I there should be an alpha over here, but in this case, the alpha is smaller than the beta, so tau, which is the minimum, equals the alpha. So depending on whatever determines the uninterrupted production time earliest, the breakdown or the maintenance, is to be taken here as tau as the uninterrupted production time. So it's this tau that we need to enter into the corresponding parameter for producing profit. And this is then, because of this renewal property, tending towards the corresponding expected value. And this can be calculated now under different conditions of whatever the typical breakdown random variable is and the corresponding estimation of it, and corresponding maybe slack time to give a certain safety margin to predate the breakdown, if this is something that can be used to an advantage. So what is our theorem? The statement that we can make is that predictive maintenance is a more profitable strategy, and we can look at preventive maintenance also as a specific type of predictive maintenance with a very rudimentary predictive model, namely a constant model. And then reactive maintenance, if and only if this technical condition is met. So what is this? Beta is the time of breakdown. So it's really the screen length of time, and it refers to the physical process and the distribution of whatever natural reactive maintenance length would occur. I'm assuming that the gain rate is always the same. So, and I'm also assuming that always there is a constant cost and repair time. So these are the simple-most cases. The only source of randomness is really in the breakdown time here. However, also I'm assuming that there's an extra idle time of the reactive case. So I'm assuming that then when I'm not scheduling the maintenance and I let things take its course and I wait for the machine to truly break down and only then start maintaining it, I have an extra reaction time, so to speak, to collect my tools and start get the maintenance process going. That's this iota hat variable, and that's so to speak the difference that I'm considering between the reactive maintenance and the predictive maintenance process, that there is this extra iota. What you see here, and this is the observations, is first observation is that the idle time, the iota, if it is equal to 0, so there is no saving in idle time for passing to predictive maintenance from reactive maintenance, then because of this exact criterion, this equivalence, this right-hand side will be zero, and the corresponding condition cannot be met with, and that means I will have a necessary lack of profitability for predictive maintenance. Let us take a look on the left side what's here. This is the difference of the expected values of the breakdown time and the time of the maintenance. So typically this should be a positive value in which this is small when it is possible to use an estimation alpha. And so you may wonder why there is a index 1 here for these parameters. This is due to the nature of the result of the renewal theory. I could have taken any other index here. All these variables are identically distributed. So I'm just taking the first. So if this identically distributed breakdown time in its expected value minus the expected value of the scheduled maintenance time has a specific value and it's small enough, and this is some number between 0 and 1, then I'm small enough, then there is actually an increase in profit by using predictive maintenance. That's what this gives us. We can arrive at such theorems easily by using these formulas for different strategies, namely in one case where this is always beta in the reactive maintenance case, and in the other cases where we have certain, where we calculate this expected value of the minimum of these two times, given only this probability of the scheduled maintenance being smaller than it. So all that is needed from the information of what the scheduled maintenance times does in dependence of the given distribution of the breakdown time is inside this probability, and all of that is needed. You see, since this is a number between 0 and 1, if this condition is true for this probability being replaced with 1, then it implies that it's true for the probability being there, being what it is. So we have a sufficient condition easily if we replace this left-hand side only by the difference of these expected values, which is handy because then I don't even need to know much about this distribution. And it gives us the second observation that if there is a positive idle time that is saved when using PDM over reactive maintenance, then there's always some precision or accuracy of the scheduled maintenance time, namely that it's sufficiently close to the true predictive breakdown time, and if this difference is small enough, then I obtain that this condition is met, and I obtain that predictive maintenance is more has a higher asymptotic profit rate than the reactive maintenance strategy. So this is the result. One can say the bad news is if you cannot save any idle time, don't try to use predictive maintenance. And the good news is if you can use it, if you can save some time by using predictive maintenance, then there's always the only thing that you need to know to be sure of is that your estimated time to perform the maintenance lies below the true breakdown time. And if this difference is small enough, then this number will be small enough, and the criterion for higher profitability of predictive maintenance is fulfilled. So there's, so to speak, a bad news and a good news. The good news is also that all one needs to know is the first moment, really. So if I have some sort of let's consider a case study, the one that we studied in the project, namely data from the ball screws. What you see here on the left side is data that we collected from forward and backward cycles of the ball screw being used over, always the same distance that it has been sliding across, forward and backward. And what is measured here is the acceleration of at certain points that accelerometers are measuring. We're using this in an offline fashion in the beginning, when the machine is still working very much as it should, to find a threshold. So we chose this threshold by lowering it until these many incidences where there is a exceedance of the corresponding extreme values here is very much uniformly distributed across the time axis. And we fixed this threshold afterwards and used it for, since it's 400, it's the same threshold, to check later if a certain amount of untypical occurrences of exceedances happen. And this has been done with several features, with the accelerometer, with the raw data itself, also with some derived features such as statistical features, like here it's the standard deviation. It turned out that the standard deviation was in itself, if aggregated over the cycles, a very handy indicator of the health of this device. And we saw that after a certain typical period, in this case it was 1 week, a single ball screw could be actually broken by this heavy load that was applied to it. So by looking at it for 1 week, we could see that there was considerable exceedances of these thresholds. This was the way we trained the model. And now for this particular case, we developed on the one hand a two-state health state classifier, but also a regression model for the remaining useful lifetime in each of the cycle lengths. So if one looked at such a week, it would be that along this time, the remaining time before the first indication of an unhealthy state occurred would be the Y value in each time case, so that it would go down and kind of predict this point of this first occurrence. And therefore, these types of, forms of predictions of remaining useful lifetimes would result. And as you see, this corresponding time of crossing the x-axis, where the remaining useful lifetime appears to be 0, has a certain inaccuracy, of course, and the corresponding estimation of this beta leads to some estimate of alpha, when then the best maintenance time should be chosen a little bit before, probably. And this leads to, as you can see, different accuracy here accuracies here lead to different values of this value. If it's not possible to choose it precisely, then this condition that we have is possibly not met with. So choosing some estimator of the time that it takes until there's a breakdown is essential to make sure that the condition of profitability is met with. One can also, the nice thing is that it's only the difference of these expected values that matter. So in a way, you can argue that it's not so important to be accurate as long as I know what my first moment is of the. So if I'm totally sure about the expected time of my scheduled maintenance, as long as it is smaller than the expected breakdown time, I have met the condition of the profitability of predictive maintenance. So ironically, it is actually for only this condition not important to be not earnest but accurate. So I, of course, just for the asymptotic profitability to meet this criterion, only this condition that actually doesn't have anything to do with the variance of the distribution of the scheduled time is necessary, but only the mean. As long as that mean is smaller than the mean of the breakdown time, I'm in business. But of course, this is where it becomes apparent that on top of the condition, the property of a process being recurring and being a renewal process, it is also, of course, a question of how quickly such a limit is assumed. And if, of course, there is lack in precision in the sense of there being a strong variance of the corresponding maintenance time, scheduled maintenance time, it will, with high probability, probably lead to the ruin of the small and medium-sized enterprise because it just takes such a long time before the asymptotic profit rate is actually reached. And this is, of course, in some sense still important, but just a condition for the asymptotic rate. If I have enough time and I can afford to wait very long time, it is actually not important to be accurate. But this kind of reminds us that maybe more accurate and more deeper results about this maintenance strategy should also be considered, namely those that relate to the convergence rate or the speed of convergence towards this asymptotic profitability rate should be also evaluated and used for evaluating predictive maintenance as a strategy. Okay, but this is where I'm stopping, and I'm grateful for your interest, and I would be happy if you asked some questions.
Thank you, Dr. Florian, for your nice presentation and explanation, starting from the types of maintenance, reactive, also in predictive. I think we have someone raise their hand. Please ask any have question. Please ask.
Hello, sir.
Sir Azafat, yes, please.
I have question. Could we use this cost model for all industries such as manufacturing and medical equipment, etc.?
Well,
Yes,
the condition
the
of
question,
the
question is to us, this
I
will
heard.
work on all type of industry, including manufacturing, medical, or other equipments. Okay.
Okay. Yes, thank you. I
Yeah.
understood. And then it's very much the question of whether the condition of renewal situation is valid here. So what this means is if you yeah. So okay. If you look at the process here, the one that we looked at, the specific industrial process, as you can see, in each cycle, things are very much the same in the sense that what happens here allows the assumption of a renewal process or being identically distributed. In fact, here you can see that there is not quite an identical distribution, or at least one which is non-trivial if it is to be looked at, modeled by this distribution. So there's some sort of switching. Of course, if from cycle to cycle, the distributions are very different, then this formula cannot be used, and some other process property should be used to maybe arrive at a similar type of result. But
Okay.
I hope that answers the question.
That's it. Thank you for the reply. Isra, are you clear about your question? Okay, any other one have some question?
Yes, sir, I have two questions.
Yes.
to ask.
Okay,
Yes,
thank
please.
you. Any other one have some question?
Yes, sir. Hello.
Javeria, yes, raise you.
Sir, my question is there any other or any different approach that is used to predict the equipment failure in predictive maintenance?
So
Well,
your voice is not clear.
I could hear. I
Okay,
think
okay.
the question
My
was
question is, okay, let me, my
You can
question
type
is
in
there
the
any
chat
different
section
approach that
otherwise.
is used? Okay, okay.
Can you say again, please?
Just type in the chat section. If it's not clear, then maybe it will clear.
What I understood was, are there some other approaches to evaluate predictive maintenance, right?
Yes, sir.
So
What are the other approaches that are used to predict the equipment failure in predictive maintenance?
yes, so the types of approaches to use a cost model is of course a specific one,
What
and
will
there
be
may
the
be.
cost model of this
Sorry, I mean,
work?
let me answer the question first, okay?
What will be the lifetime of this cost model?
Fahad, let's wait for the other question that should ask one by one.
So
okay,
the answer
Florian,
would,
yes.
My answer would be that it is specific to this approach that one is interested in the profit. So if, of course, other cost considerations are at stake, for example, how reliable, for example, something can be performed, or how often something needs to be done. For example, it may not be the case that the picture of uninterrupted production that leads to the same increase in profit in the same way. So, for example, it may not be valid that the machine is assumed to be producing at the same rate as long as it is left producing uninterruptedly, then of course a different model would also have to be used, and it is likely that not so easily a renewal process comes out. So think of for example, a machine that does produces plastic yogurt cups. It's doing this in the same way all the time. It's not changing during a production cycle. However, if you think of a machine, for example, a milling machine, that during its process reduces the quality of the result because the tool is becoming more and more used. So that is a different issue, because there it's not fair to assume that a breakdown occurs with the same likelihood after a long while of production as opposed to a short while of production. And that would not be valid to assume a renewal process here.
Okay, so thank you. Fahad, so we have the last question, Fahad, because time is over. Fahad, let's ask quickly your question.
Sir, what this cost model will be utilized in future or in current industry?
Okay, reliability means in future upcoming industries.
Well,
you mean from the new machines that we don't have currently, but question how would be the expectation to implement in future upcoming industry means new type of machines. Is this your question?
I think that's very likely. In the last 20 years, there have been 5 different cost models proposed, very much in the same spirit, also with the renewal model as an assumption. And what hasn't been studied in the same way that we do now is that we actually compare the different maintenance types with each other. So it's the way we do it is new, also because we that so far the time for a single round was always considered to be the same. So the only difference occurring in the different cost for the maintenance cycle, but also that the length of the production cycle also varies significantly, is new to our model. But it comes in various ways for a long time. And so it's a classical model to do a renewal assumption, and that will always be possible and has already been possible. So that in this way, it will always be used, but only if the assumption can be made for the corresponding process. Like I mentioned before, it is not necessary that the idea that the production happens always with the same probability of failure, but the failure increases due to the difference of the machine after some while. So that's a possible then it would not be if it's not a stationary process, it's not feasible to assume a renewal process.
Okay, thank you. Osman.
Yes, sir. Hello.
Yeah. Yes,
Hello.
Osman. How are you?
Hello.
Yes, sir. Fine. Sir, can you put some highlight on the practicality of the machine across the globe?
Practical side of
sir,
the model
practicality
on global
of the
side?
model that you have proposed across the globe.
You mean
It means for
worldwide?
multiple geographical location, like it's in Europe, in
Ah,
Asia.
In Asia,
ah,
its practicality across the globe.
okay.
Okay.
I
think maybe Florian, if you allow, I can ask because I also work
okay,
in the
yeah,
model.
I see.
Aswan, your question, because the industry are same everywhere. If it's some kind of, only the difference is the environmental factor. For example, Asia is more hot areas. In similarly, like in UAE, we have 50 degrees centigrade in outside. So there may be some factors about environmental effect, but otherwise the machine for practical implementation, if either it's in Europe or in Asia or any country, it's the same, because machinery have the same parameter, same sensor that is trained for that we could apply this cost model. So only we can think about the environmental factor. Okay, I think Florian, maybe if you want, you can add some more.
Yeah, I also think that these parameters that are always machine specific, and they may of course be different in different locations. But if you, so to speak, have a condition for its profitability that all of these parameters meet, then it's possible to use a global condition like a threshold for this difference in the expected values of breakdown time and scheduled maintenance time. And while they may differ from machine to machine and from location to location, the condition, I mean, it is reasonable to have a threshold for this value that's valid for all locations. That's possible, but it's machine specific. So or process specific. If a process is to be evaluated in this way, one would have to assess the distribution of beta and of alpha specific to that one location.
Okay, thank you. Any other one? Okay, thank you, Dr. Florian, for a nice presentation. I think
Thank
we
you
are
very
at
much.
the end, and hopefully we can continue in some future after in working in this
I hope so too.
topic in the cost model, because as per my the SMS paper that we published,